Hi students, it's Miss Schlender. I am here with you today and I'm going to be giving you the lesson on absolute dating. I'm going to talk about the DINB and what notes you should be taking. I'm also going to do a little bit of a demonstration, and then I'll give you the lesson and what you'll do for your notes. Included in this VNQ is an additional video to talk about absolute dating, and please watch that as it will help you understand this concept a little bit more with, in supplemental to that. The additional video you don't have to take notes on, but it is helpful so that you can understand absolute dating. Okay, so I'm going to start with giving you a tour of the DINB. Okay, so we are going to be doing lesson 3 today on absolute dating. Our essential question is, what is the difference between absolute and relative dating? And our learning targets is to understand how elements such as carbon can help us determine a more accurate age of rock and fossil samples. The notes that you will be taking are on this page. I'm sorry, my PowerPoint messed up those text boxes, but you will be answering the question, what does absolute dating measure? What is parent material and daughter material? And then on this side, we'll be talking about what all these different elements can decay into, which shows us about half-life, and half-life is a huge part of absolute dating. Then when we're done with the notes, you are going to be doing some questions. These questions are about half-life and will give you an example of different elements and what they decay into, and we'll be asking you some questions about that. Okay, so those are the notes. Please take notes during the video, and then when you're done, do these half-life questions along with watching that additional video. Okay, so let's start with, just trying to move myself here. Let's start with, defining what absolute dating is. So absolute dating is measuring the exact age of Earth material. Now, this Earth material could be rocks, it could also be fossils, but really you're finding out an exact age. Obviously, this is an estimate. We can't ever get things 100% right. We can get really, really close to it, but this is our best estimate of getting an exact age. This is different than absolute dating. This is different than relative dating. With relative dating, we just label youngest and oldest, or what's in between youngest and oldest. With absolute dating, we're actually able to get more of an exact age to give a number to that. So what do we do and how do we figure out the exact age of something? So that's challenging. What we do is we look at the different elements in that material. Depending on the type of material, we will look at different elements, and I'll talk more about that on the next slide. So in everything is made of atoms, and those atoms make up elements. These elements, we label them as either the parent material or the daughter material. The parent material is what is originally made in that rock or that fossil. Parent materials are unstable elements, though. That means that they will decay and break down. Daughter materials are the more stable elements. Now, elements, they always want to become stable. They don't want to stay unstable. So over time, we will see that parent material break down into its daughter material, so it becomes a more stable element. And this is actually what half-life is. So what is half-life? Half-life is the time it takes for half of the amount of unstable element to decay or change into the stable element. So basically, it's the time it takes for half of the parent material, the original element, to decay into the daughter material, or that stable element. By looking at this rate of decay from the parent to the daughter material, we can figure out the age. We can kind of work our way backwards to figure out the age of that element. So I'm going to do a demonstration with some paper and scissors. Just let me make my camera a little bit bigger so you can see what I'm doing. Okay, so I have my paper here. This is just a 8 centimeter by 8 centimeter paper. And I can think of this paper as the parent material or that parent element of rock or fossil. For this example, I'm just going to say that this is carbon-14. Carbon-14 is a very common element found in plant and animal remains. Okay, so this usually comes from organic things, and we use carbon-14 to help us with fossil identification. You may have heard of carbon dating, so that's kind of relates to that. Anyway, so this is carbon-14, and this animal or plant just died, and it's just becoming fossilized. Now, I'm going to fast forward, though, a few thousand years, and I'm going to do the half-life of this. So when we fast forward a few thousand years, and I cut this in half, maybe I should fold it. I'm going to do the half-life of this carbon-14. I'm going to cut it in half. Okay. And now that carbon-14 splits. So this is the parent material over here. This is the daughter material. Carbon-14 decays into nitrogen. So the daughter material comes from carbon-14, then becomes nitrogen. I'm going to put this off to the side, and that nitrogen is just going to sit over there. I still have my parent material. Now, if you're looking at this, can I cut this again? Probably. So I'm going to do another half-life. I'm going to fold it, and I am going to cut it again. So that carbon-14 is becoming less and less, and we are getting more and more nitrogen, or that more stable element. So here's my nitrogen. It's going away from that carbon-14, and this is what I have left. Now, it's still a little teeny tiny box. It's a lot smaller than it used to be, but can I cut this? Yes, I can. So I'm going to fold it in half, and I'm going to cut it again. Another half-life. So far, this is my third half-life that I've done, and this is thousands of years later. All right, here is my nitrogen. That is the daughter element of carbon-14, and this is all the carbon-14 I have left. Can I cut it in half? Yes, I can. I still can keep going. So I'm going to fold that carbon-14 in half, and I'm going to cut it. All right, there's another half-life. That's our fourth half-life. That becomes nitrogen. I'm going to put that in my nitrogen pile. So let's look. Let's see. I have all of this nitrogen here. Look at all that nitrogen, right? And this is all the carbon-14 I have left. My nitrogen pile is big, and my carbon-14 is tiny. Could I do another half-life? I probably could. All right, so I'm going to cut this and fold this in half. So far, I've done 4 half-lives. Now we're going to do our 5th half-life. Goodbye, little carbon-14, and here is my nitrogen. I'm adding it to my nitrogen pile. This is all I have left. Can I keep going? Yes, I can. If I'm really, I probably need smaller scissors soon. Okay. All right, cut that in half. There's a half-life. Boom. That carbon-14 becomes nitrogen. And if I really wanted to, I could cut this in half again, and I could keep going and going and going. I think you get the idea. So, basically, this used to be a big square, and we've done multiple half-lives on it, and this is thousands of years now. And the ratio to nitrogen versus carbon-14, there is more nitrogen than there is carbon-14. I'm going to show you what those piles look like. Okay, so here is a picture over here of what is left of my carbon-14 versus what we have now of nitrogen after doing 6 half-lives. So I cut that paper 6 times. I could have kept going, but I didn't. Really, I could keep going forever because, like, if I even break it down to molecular level, I could keep cutting those molecules in half and half and half. But anyway, so we did it 6 times. Now, carbon-14, as we can see, there's not a whole lot left of that, but we have a lot of nitrogen left. What we do when we are doing absolute dating in a sample, we see how much of of the daughter material is left versus the parent material. We find that ratio. As we can see, we have a lot more nitrogen versus carbon-14. So it's like a 6-to-1 ratio, as we can see here. Now I can take that information. Scientists know, and we know that the unstable material takes many thousands or millions of years to decay. And we know that carbon-14 takes 5,730 years to have one half-life. So to do that very first cut, takes 5,730 years. So that's just one half-life. Now in this sample, for this example, I did 6 half-lives. So what I do is I take that time that it takes to decay just one time. So that's 5,730 years times 6 half-lives. That means that this sample, or this example I did, represented 34,380 years. So let's pretend that this was a fossil, and I was looking at the ratio of nitrogen versus carbon-14 and like how much was there. I saw that it represented 6 half-lives, and I can figure out that's the absolute age of that fossil. I can say with confidence it's about 34,380 years. Okay, so that's just a demonstration to show you what half-life is. We have that unstable parent material that's originally there. It takes many thousands of years for it to decay into its stable daughter material. Over time, we will have more of that stable material versus the original unstable parent material. Okay, so carbon-14 is just one example of this though, and carbon-14 is really good for fossils and really good for living things, but as you probably guessed, rocks are not alive, so we don't have carbon in rocks as much as we do with other living things. So I'm going to go through a few examples and you should type this in your notebook, but as we talked about carbon-14, that decays into nitrogen, and it takes 5,730 years, like we said. Carbon-14 is good for living things that are less than 50,000 years old. After that, it gets pretty difficult to detect, that ratio, because that carbon-14 is so small at that point. But this helps us date fossils that are younger than 50,000 years old. Now we're going to talk about some examples that we use for rocks, because rocks, as we said, carbon isn't really a good way for us to determine the age of rocks, and rocks can be a lot older than fossils of living things. So the first element that we use to help determine the age of rocks is rubidium. It's hard to pronounce, but rubidium-87, and this decays into strontium. I know, element names are super fun. I can pronounce the rest of them, I promise. Anyway, so it takes 49 million years just to have one half-life of this. So it takes a really, really long time for that paper or that original parent material to be cut in half. This is helpful for us to determine the age of rocks that are less than 100,000 years old. So this is kind of good for relatively younger rocks. Another example, I know I can pronounce this one, is potassium-40. Potassium-40 decays into argon. So this is good for rocks that are still also less than 100,000 years old. But for potassium-40 to decay into argon just one time, right, one half-life, takes 1.3 billion years. So that's a really long time for it to decay. And then our last example is uranium. Uranium-238. This decays into lead-206. And this one takes the longest to do a half-life. It takes 4.5 billion years. So this is good for really, really old rocks, and this can help us determine rocks that may have been around since my computer glitched. These are really, really good for the oldest rocks that we can find. Okay, so these are just examples of different elements that we can use for half-life calculations. We already talked a lot about carbon-14, so I'm not going to spend too much time on this slide. You don't need to write this in your DINB. But carbon-14, like all of those other elements, they are radioactive, meaning that it's unstable. We see here that carbon-14 changes into nitrogen, that other element, and it takes about 5,730 years to do that. So anyway, we already talked about that, but I kind of liked this picture to show that change from carbon atoms into nitrogen atoms. Okay, now I'm not going to play this video. You do have some questions to help you calculate half-life. Some of them will have graphs where you're going to be looking at the decrease of an element over time. And so this is really similar to one that you're going to be looking at, the rate of decay. You have to see where so basically here, this would be the first half-life where they intersect. And then after that, we're going to have more of that daughter material and less of that parent material. Ooh, I like this GIF. I forgot I had this. This just kind of shows that pattern of over time we have more of the daughter material, less of the parent material, because we keep cutting that original material in half and half over and over again. Okay, so at this point, watch that other video that's attached to this. Sorry, I know this one was a little long because of that demo. And then when you're done with that, don't forget to do the quiz. And then don't forget to do, I'm going to zoom back here. Don't forget to do those half-life questions. There's 3 of them. And this is a good way for you to practice comparing what would happen and calculating that absolute age of a rock or fossil. Thank you for watching. Have a great day, everybody.